Good evening, everyone. My name is Rahul Maddimsetty. I'm an engineering director at Foursquare here in New York. I'm in charge of the Places database and API team. And my team is basically responsible for the systems that, that produce our database of over 105 million places worldwide, both from first and third-party data sources, as well as the platform that enables third-party developers to access this data either via the API or through flat file deliveries. I assume most of you are kind of familiar with the concept of clustering, but I'll state in a nutshell what it is. Clustering is essentially the process of grouping together similar objects in a data set. Sometimes this grouping together is the end goal, as with like market segmentation or similar exercises, and at other times it's this intermediate step that enables further analysis of data sets. There are several well-known clustering algorithms. They tend to be classified as like connectivity-based, centroid-based, distribution-based, or density-based. And I have a couple of examples, one of each kind. There's agglomerative, k-means clustering, clustering using Gaussian mixture models, and then DBSCAN, which is what I'll be talking about today. I have to admit, who over here has heard of DBSCAN at all? Some of you have. How many of you knew DBSCAN was an acronym? I didn't. I always assumed that it's like scanning a database. It seems like in order to accomplish anything, that's like the first conceptual step. But no, it actually is an acronym, and unlike all those heavily contrived acronyms that you come across, this one describes exactly what it does. So it's density-based spatial clustering of applications with noise. Maybe the applications was a bit forced, but DBSCAN doesn't quite work. It's been around a while. This was first proposed in 1996 in a paper that I believe has gone on to be among the most cited data mining papers of all time, received something called the Test of Time Award at the SIGKDD conference in 2014. We'll keep returning to this diagram quite a bit as I keep defining terms. But even as you look at it, I think it's pretty useful to set up the intuition behind the DBSCAN algorithm, because as you look at it, you think, you know what, everything but n should be part of a cluster, right? And that's probably because, without you realizing it, your brain is scanning for clusters using some measure of density, and that's exactly what DBSCAN does. The first definition is something called a core point, right? So in the DBSCAN algorithm, any point that has at least min points, neighboring points, including itself, within distance radius is said to be a core point, right? So the DBSCAN algorithm takes two parameters, min points and radius. And these are the only two parameters that it takes. So to return to the diagram for a bit, over here min points is 4, and the red points are core points because they're all within some radius, that is hard to define on this slide, but within some radius of at least 4 points, including themselves. Right now, although this is a slide showing a diagram in like two-dimensional space, much of what we're discussing applies to any arbitrary n-dimensional space. Next, there is the notion of reachability, which in the original paper is defined fairly elaborately. There's this notion of reachability between a pair of points, which is not a symmetric relationship, and then there is something called density reachability, which is. We can skip over those details though. Let's just suffice to say that a reachable point is something that is within distance radius of some core point, but which doesn't qualify to be a core point itself. Right, so over here, that's the points B and C, they're in orange. And so by exclusion, any point that is neither core nor reachable is considered an outlier. Right? Outliers, again, intuitively shouldn't be part of any cluster. Over here, that's a single blue point, N. So given these definitions, you can think of a cluster as collections of core points and the points that are reachable from them. Now, the diagram that I showed you had just one cluster in it, but it's fairly easy to see how this generalizes to a data set that contains several clusters in it. This is actual Scala code from the Foursquare code base. I didn't like obfuscate, clean it up, or do anything of the sort, right? This is exactly what we have in our code base. It's an implementation of the DBSCAN algorithm. So we'll step through it a little quick. If you haven't read Scala before, it'll befuddle you. So we'll step through it. So right up on top is the inputs. There's a bunch of points. There are the parameters, radius, and min points. Over here is where we have the outer loop, as I shall refer to it. We will loop over the points, skipping over anything that we've already visited. As soon as you visit a point, you mark it as seen, and then you find all of its neighbors, right? In order to do that efficiently, we have a KD tree up here, and specifically we use a geo-KD tree, which is aware of distances on the Earth's surface. It can take a distance in meters and then find points, as opposed to just XY coordinates. So we then do a density check. Having retrieved neighbors, you just need to compare that number of neighbors to min points. That is our density check. And if that is greater than or equal to min points, it is a core point, right? So anything that isn't a core point, you skip for now. There is the possibility of rescuing it afterwards, but you treat it like it were noise, right? If it is a core point, on the other hand, you kind of enqueue it to be explored. And then you have this inner loop that keeps going while the queue is not empty. You find the neighbor of the first, find all neighbors of the first element in the queue. You do another density check. If it is a core point, then you enqueue all of its neighbors as well, right? If it isn't, you don't. But regardless, you add it to the current cluster if it isn't already part of a cluster. When you get to this point, it's because the queue was emptied, so you're done with the current cluster. You can move on to the next point in the outer loop. And when you get here, it's because you're done with the outer loop. You just return the list of clusters that you've built up so far, and anything that is not in a cluster at this point is an outlier or noise, so you return that, right? So DBSCAN is an intuitive but also a fairly versatile algorithm, and it's great because unlike k-means, for instance, which some of you might be familiar with, you don't need to know beforehand how many clusters are present in the data. It's good because it can find arbitrarily shaped clusters, and because the notion of noise is so central and is like baked into the algorithm itself, it's especially well suited to when you don't want to include outliers inside a cluster. And finally, like I mentioned earlier, there are just 2 parameters to tune, so that makes evaluating models a bit simpler. This is just a quick illustration of some of the more arbitrary shaped clusters that it can find. The one on top is like non-linearly separable. DBSCAN can detect those clusters, and you also see points that don't make it in. Those are noise. And the figure below shows you on the left the output of k-means, and on the right the output of DBSCAN, and you see that DBSCAN does a better job. It has its disadvantages as well, and as we were looping through the code, stepping through the code, you probably realized that the actual clusters that are output by the algorithm could depend on the order in which the points are processed, and this makes DBSCAN non-deterministic in some cases. Now, the core points will always be part of the same clusters regardless of order, but the reachable points, especially if they're reachable from more than one cluster, they can end up in different clusters depending on which core points came first in the outer loop. This isn't always a bad thing, but it's just something to be cognizant of. Now, another advantage of DBSCAN is that it doesn't work great on data sets where density varies greatly, and this is because there is no single value of min points and radius that would work well across all of the data set, right? So this is where we end our generic high-level treatment of DBSCAN and move on to how we use it at Foursquare, right? So like the title slide said, if you had the time to read it, we use this to improve the accuracy of our venue lat longs. By the way, venues are just what we call places in our database. So eBay NYC is a venue, as is probably that Marshall's Manhattan that I see, right? So anything can be a venue, and venues have lat longs, and we want those lat longs to be as accurately placed as possible. So historically, we would try and determine the best lat long for a venue by periodically recomputing the centroid of the check-ins that a venue had received over time, and then just hope for the best. Now, the problem is that check-ins are inherently noisy. And I'm not talking about GPS accuracy because, I mean, that's a whole other problem. But even if GPS accuracy were to be perfect, which it is not, the problem is that the behavior that generates the check-ins themselves, that is noisy. So what do I mean by that? Most users, they check in when they're physically at the venue, right? But sometimes they check in from a parking lot, or they check in from across the street as they're walking in or out of the venue. Less frequently, but I guess still often enough that this is a problem and I know about it, is that we have users that try to cheat at the game, right? And so they may check in from somewhere else entirely in order to earn coins or unlock stickers or become mayor of a place. And so we have simple checks to try and detect obvious cheat check-ins, but we also have some very motivated and persistent users who have been known to gradually check in from further and further away from the center to A, thwart our cheat detection, and B, gradually move the centroid closer to wherever they want it to be, I guess. Honestly, with the things that I've seen, there is nothing about user behavior that can surprise me anymore. So this is just something we need to live with, regardless. The observation was that check-ins are inherently clustered because of the underlying patterns of user behavior that generate them, right? So the idea was if we could find clusters of check-ins and then use the centroid of just the dominant or the largest check-in rather than the centroid of all check-ins, then maybe that would give us a better lat long. And the hope was that the dominant check-in cluster that we found would correspond to the check-ins that originated from inside the venue. Now, we also expect that there will typically be smaller clusters that correspond to legitimate check-ins from the parking lot or from across the street, and anything else is noise for our purpose. There is a problem, though. The problem is essentially what we noted earlier as a disadvantage of DBSCAN, which is that the distribution of check-in densities varies significantly across the world. It tends to vary as a function of venue shape and size, which in turn depends on category or chain. It depends on where the venue is located in the world. So for instance, the check-ins, if you were to visualize the check-ins at a suburban Target, that would look very different from a bar in Manhattan, for instance, right? So there is no single value of min points and radius that would work across our entire venue database. But we worked around this by training a multi-output random forest to predict the best parameter values for each individual venue given a feature vector that included, among several other things, the category and where the venue is located. Right? And we then fed these parameters to the DBSCAN algorithm to detect clusters and then recomputed the lat longs of tens of millions of venues this way. So before I jump ahead to the results of doing this, I want to just establish how we define lat long accuracy. Right? So for our purposes, a venue's lat long is accurate if it is within 50 meters of its real-world location and on the same side of the street. So that latter requirement is especially important if you want to avoid routing people who've asked for directions to the place on the wrong side of the street, or telling them to stop because the destination is on their left versus on their right, especially if it involves a U-turn. It's kind of painful. Anyway, so this is also the condition that, as it happens, our lat longs were failing more frequently as part of the accuracy test. So what we did is we built up a ground truth data set from a sample of around 1,000 venues from across the world in a variety of categories. And for each of them, we had a member of our internal ground truth team draw the true shape of the venue, as in the actual outline of the venue as a human may see it, as well as the shape of the street block that surrounds it. Now, the first shape is used for the first part of the test, which is a point within 50 meters of the real world location, so inside of a 50-meter buffer around the polygon. And the street block shape is for the second condition. So if you think about it, if a point is inside a street block that contains the venue, then by definition, it must be on the correct side of all enclosing street segments, right? So to go through some actual examples, this is a hair salon in Greece, I believe. This green polygon is the actual shape that we determined for the venue. You can see the check-ins as blue dots. And this is our street block shape. Again, this is a car wash in Turkey, and this is the street block shape. Now, you might have noticed with both of the street block shapes, they seem to include some streets in them. That's actually because our definition is only concerned with public streets. So if they're private streets, which might show up on a map, or if they're pedestrian-only walkways, they will still show up on a map, but they don't really count for our definition of being on the correct side of all streets. I guess our definition is a little car directions or driving directions specific. or centric. Regardless, once we'd done this, we needed to synthesize the training and validation data sets for our random forest models. So the way we did this is by enumerating for every venue in the ground truth data set all possible min points and radius values, using them to cluster and then compute the dominant cluster centroid, and then only use rows that resulted in accurate centroids as per our definition earlier, right? So this could result in potentially multiple rows per input feature vector. And once we did this, we did like a 90-10 training validation split, which I know sounds a little unconventional, so I'll explain myself in a bit. The reason we did this is the alternative may have been the more traditional 70-20-10 training validation test split. If we'd done that, we would have had just about 100 venues in our test set. And we figured that testing didn't necessarily need the actual shapes. So one, the process of acquiring more shapes and actually precisely drawing them using internal resources is fairly expensive and slow. So we decided to use a crowdflower job instead, where we could just have them make the judgment of whether or not the new lat long was better than the old lat long without having to draw a shape to determine that. And we were able to do that with far more venues. The job looked something like this. It kind of shows you the old location in yellow, new location in green, I believe, and asks, given these definitions, which of these is better, right? So final results, I believe, were a net improvement in lat long placement of 37%. Yeah, that's right, about 37%, which is pretty significant, and like it beats by a mile any previous attempt that we've made to make progress against this specific problem. These are a couple of venues where, again, you start to appreciate how check-in density can factor into this problem. So you've got some place that I guess looks somewhat suburban, and another place that's in a slightly more packed area, and the check-ins are a little more scattered in one case and a little more dense in another. But we still manage, using this approach, to pull the map pin over to the correct side of the street. So that's pretty much everything I had. I just wanted to acknowledge that all of the work I just presented was actually done by people on my team. I'm just presenting it. Right? So if you ask me difficult questions, I may not be able to answer them, but I'll try. All right? Thank you all.
Thank you very much. Time for Q&A. Let's start in front and move back. Hi, I'm Frank.
Hi.
Could you go into more detail about like which features you looked at when you were using like feature vectors?
Oh, the feature vector for the venues? Sure. As it happens from previous work that we've done to improve not just like the quality of our lat longs, but also the quality of our categories, and a reality problem, which is just because we are a crowdsourced database of places, we frequently have places that are created that are not real world places. You know, like people create places as a joke or like miscategorize them as a joke. And so there's been previous work done to try and extract a large number of features. We have like tens of them, I want to say like 50 or 60 maybe, right? That includes things like how many people have checked into this venue, how many how many check-ins have we had totally, how many unique visitors have we had, several geo-normalized variants of the same signals, like we have for every top-level category, we have like one feature. So is this like a food or nightlife place? Is this like a shop or service? Is this something else? And the random forest just learns the significance of each of those features. We have features, I believe, that have to do with category, like I said, possibly whether or not a venue is part of a chain, stuff that has to do with, I don't know, I'm thinking of my feature. I think when it was last edited, a couple of things like that. There's several features, I don't remember all of them now, but things that we hope would indicate inherent properties of a venue, like is this a big venue, a small venue? Is it visited a lot? Is it not visited enough? Like the reason I said earlier that we recomputed tens of millions of venue lat longs versus like the 105 million plus is that some cases we just don't have enough check-ins to be able to determine or to find clusters, right? So, so I'm not sure that answers your question. That's like as many features as I can recollect right now. Right. Yeah. Hi.
So just out of curiosity, do you guys like
how many people know? I don't know, like for example, like nearest neighbor assignment. Like, you know, like assign you have some ground truth and assign like, you know, like the ones that they go the closest distance to that.
How do you foresee that generalizing to venues where you don't have the actual ground truth shape?
So you can have the, like, I don't know, like one polygon the menu shape and
right.
nearest location to that.
Oh, I see. I think I know what you're talking about. So maybe this answers your question, but there's work that we've done previously outside of my team even, which is to try and determine two-dimensional Gaussian distributions of check-ins. And I suppose what you're saying is we could use, for instance, whatever shape 90% of our check-ins are as like...
I'm pretty sure that what you guys are doing is better. I was just curious how the performance of that is. Like, you know, how much better is that? Like, you know, is that
all right.
better or like...
To be fair, we didn't try that exact thing in this case. We have considered, I think, using those shapes that they're probabilistic shapes that we have, and we've considered using them. But not in this iteration. When I said earlier that this beats, you know, by far anything that we've done previously, I think what we did previously was along a couple of lines. We tried filtering out check-ins that seemed bad. There was I remember very specifically, there was this point where bad lat longs from old BlackBerry devices were like throwing off our lat longs by a huge amount. So we just filtered them out altogether. Similarly, we filtered out check-ins that were before a manual edit had been made to the venue's actual lat long, and only used like check-ins that came afterwards. Suffice to say that our approach was like just continue to use the centroid of check-ins, but just filter check-ins that you think are outliers, right? I guess that's what we were trying to do, and DBSCAN turned out to be a better way of doing the same thing. That's the only thing we've tried, and we are like, by some measure, 37% better, I guess. Sorry. I think he was before you. Sorry. Go ahead.
Yeah, so your response just now actually somewhat answers my question, which was going to be like, as GPS in our phone gets more and more accurate, like, how do you rehandle the same existing data, or like how that accuracy of data changes?
That is a good question. I'm not sure I'm the best person to answer that. There are other people at the company who are thinking about that problem. What I didn't mention is that when we get check-ins, we get a latitude and a longitude, but we also get a horizontal accuracy, which for now we don't consider as part of any of this computation. We considered doing it. Like, what if rather than just a point, we used like circles and tried to like do something fancy with overlap? I guess it was one of those fancy things that we didn't get around to doing because a simple thing worked better. But yeah, looking ahead into the future when GPS accuracy improves significantly, I think it solves the problem. It solves one component of the noise of check-ins. It doesn't solve the fact that people don't necessarily always check in when they're actually at the venue, and the fact that people are going to cheat, right? So there's noise from legitimate check-ins, and there's noise from not so legitimate check-ins. But regardless, I feel like having higher GPS accuracy only solves like part of the problem. Sure, go ahead.
Do you have any examples of where DBSCAN would not perform well, or maybe exceptions to this use case?
Yeah, this is one of those questions where I wish somebody on my team was here. But the one thing that I do know is that there are just cases where DBSCAN would not be able to detect clusters in the first place, right? Because you specify a value of min points and radius, and there aren't enough check-ins to meet that, right? So in that case, we do nothing. We just stick with the lat long that we have already. And to be clear, like our lat longs were not terrible before. They had problems, and you know, this helped us get better with them. So yeah, I don't know that it answers your question necessarily, but right.
Did you guys find any patterns as far as the bad check-ins? You know, the big venues versus small venues. So, you know, things like, is there more bad check-ins associated with big venues versus small venues, things like that?
I'm sure those insights are possible to extract. We've not like specifically noticed them. It's just, of course, the greater the number of check-ins at a venue, the more likely that there will be noise in it. But also, I think that's one of the advantages of just throwing stuff at a random forest and like not having to look on the inside, you know, to see what it learned. So the short answer is no. There's no pattern like that sticks out that I remember my team mentioning, but maybe they did.
No.
Someone at the back.
You mentioned something about geographical differences. What do you attest that to, and how did you address that? Is it more geomagnetic? Is it because you're using different cell carriers and GPS is different?
Oh no, actually, it's just like I said, urban versus rural, right? So one thing that happens a lot is that GPS signals bounce around buildings, right? So the kind of problems or the kind of noise that you'd see with signals in urban areas is very different from what you'd see in rural areas. That's one part of it. The other part is just that there are fewer venues in the first place in a rural area, so associating a lat long to a venue becomes kind of easier, versus somebody could actually be at the venue next door in a city, and like the distances are so small between venues that it could make a difference. And so your centroid could end up being, or like streets are narrower, for instance, and that places you on the wrong side of the street. It has everything to do with just density. So it comes down to whether it's urban or rural or something in between.
I actually have one question. You mentioned ground truth.
Yeah.
What did that look like in your context? Was that employees running around New York?
Oh, no, not at all. This was from all over the world. So mostly relying on satellite imagery and other forms of web research to try and establish where a place really was. In some cases, we can't determine it. So you just let go and you move on to the next thing. So 1,000 venues is a lot for a small team to do, right? So, like I said, it's slow and expensive.
One more question. So in your model, you have a polygon for the venue and
yes.
another polygon for the streets. But there were also a lot of check-ins. In one of the screens, it looked like a freeway, and then there is a venue, and then there are streets.
Yes.
So you were taking into account all of the streets, and leaving out all of these check-ins on the freeway, which is actually much closer to the street that is way back to the venue.
I could go back to, this is what you're talking about, right?
Yeah, so if you see here, we're taking into account the last check-in there on the street, but there were also a lot more check-ins here, which is, if you take the distance into account, this is almost like in the same radius.
Okay.
So, while looking at this screen, can you think of any other model you think you can apply as far as improving the accuracy?
To be sure, I'm not positive I fully understand your concern, but so here's the thing, right? Like the shape only factors, or rather enters the picture when we need to use this particular row of ground truth to inform what valid outputs are for the random forest, right? So we would iterate over a number of possible values, and then it would end up detecting different clusters as a result. And if the largest cluster, it's not throwing away anything outside of the shape, in case that wasn't clear, right? It's just using every check-in regardless. It's just using different parameters. And if the centroid of the largest cluster that results from that particular set of parameters happens to be within 50 meters of the real shape, which was on the previous slide, or inside of this shape, then we'd consider it good, right? So we're not throwing away anything outside of the shape. Again, like I said, with unseen venues, we have no way of knowing what the actual shape is.
Sure.
Yeah.
Just to piggyback on this question, this looks like it works like in Western countries. I'm wondering, what about third world countries?
They were included. They were included in this. I mean, this is Turkey, and there was Greece before, but we've done this to include like Vietnam and a bunch of others. Like, they're all over the world. This is not just, this isn't just the developed world.
Okay, so you guys would use the same algorithm as in Africa or
Yep.
that?
It still works.
Accurate.
It still works conceptually. Again, it is reliant on having enough check-ins in the first place, and then maybe in some places we don't meet that minimum, but where we do, it does a better job than if we just used all the check-ins, right? So it's incremental, but it requires that we have enough check-ins in the first place to be able to detect clusters. Done.
Well, thank you
All
very
right.
much. That was fantastic.
All right. Thank you.
Good start to the evening.
All right.